Hi everyone, and thank you for being here today. So today I'll be presenting our project titled BRIXGLASS, Enhances Subgrade Strength and Reduces Moisture Susceptibility. Now, to put it simply, this project is about finding a smarter and more sustainable way to strengthen the soil beneath roads by using recycled waste materials, such as crushed bricks and glass powder. And what makes this especially interesting is that we're not just improving soil performance, we're also helping reduce construction waste at the same time. So first, let's start with the issue we're trying to solve. As we all know, Malaysia experiences heavy rainfall quite frequently, especially during monsoon seasons. And while rain may seem harmless, prolonged rainfall can actually cause serious damage to roads and infrastructure. We often hear about roads cracking, sinking, or even collapsing after heavy rain. But what many people don't realize is that the actual problem doesn't begin on the road surface. It starts underneath it. Why it happens? Now, the reason this happens is because rainwater slowly seeps into the soil beneath the pavement. And as that soil absorbs more moisture, it gradually becomes weaker and softer. Eventually, it loses its ability to support the load above. So when the soil underneath weakens, the pavement above also starts to fail. To put it simply, if the foundation is weak, the road cannot remain stable. Now we go to failure process of pavement. If we break the process down step by step, this is how failure happens. First, rainwater enters through cracks or small openings in the pavement. Then, that water reaches the subgrade soil underneath. As moisture continues building up, the soil starts losing strength and stability. And finally, the pavement above begins to deform, causing rutting, settlement, and, in severe cases, total collapse. So as you can see, moisture is one of the biggest threats to pavement performance. Now, traditionally, engineers solve this issue by stabilizing the soil using cement or lime. And yes, these materials are effective. However, the downside is that they are expensive, produce high carbon emissions, and are not environmentally friendly. So while they improve engineering performance, they create environmental concerns as well. Because of this, many researchers are now searching for greener alternatives. So, moving on to our objectives, our study focuses on three main goals. First, we want to evaluate how much these recycled materials can improve soil strength. Second, we want to examine how durable the stabilized soil is under wet and rainy conditions. And third, we want to identify the most effective mixture ratio for the best performance. Now, let's talk about the materials we used. For this research, we selected two recycled waste materials. The first is crushed brick fines, which come from broken construction bricks. And the second is waste glass powder, which is made by grinding recycled glass into fine particles. What's interesting here is that instead of letting these materials go to waste in landfills, we reuse them to improve soil quality. So, in a way, we're turning waste into a useful engineering resource. Now, you might be wondering why choose these materials. Well, there are several reasons. First, they are inexpensive and easy to obtain. Second, they are environmentally friendly compared to traditional stabilizers. And third, they help improve soil properties while reducing waste disposal problems. So overall, they offer both engineering and environmental benefits. Now, moving on to the compaction test results. Based on the Proctor test, we found that increasing the amount of stabilizer improved the dry density of the soil. For crushed brick, the highest dry density was achieved at 20% addition, reaching 1.81 grams per cubic centimeter. Similarly, for waste glass powder, the best result also came at 20%, with a slightly higher value of 1.82 grams per cubic centimeter. So as you can see, both materials improved compaction performance, but waste glass powder performed slightly better overall. Now, if we compare the behavior of both materials more closely, we notice an important difference. Crushed brick required more water during compaction. This is mainly because its porous texture absorbs more moisture. On the other hand, waste glass powder required less water while still achieving higher density. What this suggests is that waste glass powder compacts more efficiently and may be better suited for moisture-prone environments. Another major benefit is moisture resistance. What happens is that these stabilizers help create a stronger internal structure within the soil. This structure reduces water penetration and prevents excessive moisture retention. As a result, the soil remains stronger even under wet conditions. And this is especially important in countries like Malaysia, where rainfall is consistently high. So, overall, BRIXGLASS provides several key advantages. It improves soil strength, it increases durability, it reduces moisture-related damage, it lowers construction costs, and perhaps most importantly, it supports sustainable engineering practices. So compared to traditional stabilizers, it offers a much more balanced solution. Now, one of the most exciting aspects of this project is its sustainability impact. By reusing brick and glass waste, we reduce the amount of materials sent to landfills. At the same time, we reduce dependence on cement production, which lowers carbon emissions. So this project doesn't just improve roads, it also helps protect the environment. And that's something increasingly important in modern engineering. In addition to that, our project also supports the Sustainable Development Goals. Specifically, it contributes to SDG 9, which promotes resilient and sustainable infrastructure. And it supports SDG 12, which focuses on responsible consumption and waste reduction. So, beyond technical performance, this project also aligns with global sustainability initiatives. So, to wrap everything up, our study shows that crushed brick fines and waste glass powder have strong potential as alternative soil stabilizers. They improve subgrade strength, reduce moisture susceptibility, and offer a more sustainable solution compared to conventional materials. And most importantly, they show that waste materials can be transformed into valuable resources for infrastructure development. Thank you very much for listening.